My name is Christian Bayens, and today I will be talking with you all about a collaborative project between Georgia Tech and Rutgers University down in the United States called See No Evil, Hear No Evil, Feel No Evil, Print No Evil. Now, kind of an elevator pitch version of this, what we're going to take a look at is a industrial 3D printing workflow in which we don't trust anything about the network, the PCs, or anything like that, and we're going to look at the physical side channels of the 3D printing process to be able to verify that our print carries out the way that we want it to. Now, as you can imagine, 3D printing is a pretty hot topic within the industrial manufacturing realms. And so nowadays we see some big companies up here such as NASA, biomedical companies, SpaceX, and they're moving beyond just using 3D printing as a prototyping tool, but actually using 3D printing to create parts that will be used in manufacturing. So in this industrial setting, what might this workflow look like? So first of all, you've got Bob here. Bob is a designer, and he creates some 3D design. And he's going to send that design over some network to a third-party printing company, or if it's a large enough business, maybe a different department or something like that. And the design is going to be sent to a PC controller, which then connects to a 3D printer, which prints Bob's 3D object. Now that object is going to go back to Bob, and Bob will do some quick checks. He'll say, I want to make sure the external dimensions are correct. I want to make sure that the scaling wasn't wrong. And so he'll take a good look at it, and he'll say, all right, everything looks fine. He'll put it into his manufacturing process. He'll use the part, and he'll say everything's good. But we want to consider where all of the points of risk are within this process. So first of all, we're going to go ahead and we're going to trust Bob. Bob is good to go. But that network that Bob's going to send his design over to that third-party printing company may be compromised, may have a man-in-the-middle attack, some kind of issue going on. The controller PC itself may also be compromised, as well as the firmware on the printer itself. In fact, there was some previous work that we checked out where using malicious firmware, a group was able to have a cube design sent to a 3D printer, and the printer would itself print out a pyramid, which is not something you want. So all of this results in what we refer to as a malicious print. It's important to keep in mind that even if we're on a safe network and everything like that, this could also fall into the realm of user error. But either way, the malicious print gets sent over to Bob. And remember, Bob's going to check out the external dimensions. So if he is expecting a cube and gets back a pyramid, he'll be able to tell that, and he'll be able to tell if the scaling's wrong. But consider if the malicious print were to change something on the inside. So the inside is supposed to be high density, and the malicious attacker changes the code so that the print ends up at low density on the inside and ends up failing when used in whatever production. Bob won't necessarily be able to see that just by looking at the outside of his print. So what can we trust? We don't trust anything that I just discussed, but there are some things that have to happen when the 3D printer runs. First of all, 3D printers have lots of moving parts, actuators, and so forth, and so there's going to be an acoustic signature that goes along with printing whatever comes out. Also, even if you're able to fool the controller PC into appearing as if you're printing something benign, the actuators have to move in a certain way in order to print your malicious print. So we're going to check out the spatial dimensions. And finally, Bob may be able to work with a trusted material supplier to send some type of embedded material over to the third-party printing company. And we can use some fancy material science that we'll talk about later to further verify that the print is what Bob expects. So putting all these together, we form what we call a 3-layer approach. And for the sake of this talk, I'm going to separate these into 2 buckets. The first one is real-time verification. So we look at the acoustic and spatial monitoring of the 3D print. These are things that happen in real time while the print is going on. And there's the post-production where we can look at some of these material science methods after the print has completed. And we'll keep these down here for keep everybody on track. Now, just a bit of motivation for this. We have a scenario that we call the Golf Wars. And in the Golf Wars, we have a golfer who's a famous professional golfer, and we'll call him Timmy. And Timmy, due to old age and possible sports injury, his doctor has told him that he's going to need a prosthetic knee. Now, I mentioned there's a lot of 3D printing research going on in the biomedical industry, and it just so happens that Timmy's knee, prosthetic knee is going to be 3D printed. Now, Timmy has a golfing rival. We'll call him Vinny. And Vinny is, along with being a golfer, he's also very tech savvy. And he knows that Tommy's knee is going to be 3D printed, and he's going to be able to get into that network and potentially mess with that knee so that it fails, keeping Timmy from being able to compete at golf. So very important motivation there. So first of all, we got our real-time verification, and let's jump into the acoustic layer. So there's been some interesting previous work with acoustics in 3D printing, and mostly what those focus on is the acquisition of intellectual property. So training off of the acoustic waveforms of the specific motions of the printer allows you to reconstruct some arbitrary outline that the printer might produce. And so we turn that around and we say, instead of training on the motions of the printer itself, we want to take a holistic approach and say, what is the acoustic signature of the entire print from beginning to end, including complicated infill structures, which may be more difficult to track if you're just saying, what does back and forth sound like front to back? And the way we do this is we simply take a microphone and we print an object. Now, the acoustic signature of that entire object printing may take upwards of 1-2 hours, very long process. And so we split that into indexed segments, and we index those in chronological order. Then the classifier that we use is similar to if you're familiar with Shazam or SoundHound, where you're able to use your phone and listen to a song, and it tells you what that song is. We're essentially using an open source version of that. So for each of these segments, aka songs, we're going to find the spectral peaks, the temporal location of those peaks, and the distance between adjacent peaks, and form what we call a peak constellation. The metrics of that peak constellation are stored in the database. So the database represents the printed object itself, and each quote-unquote song stored in the database is a segment of the acoustic profile. So on the classification end, we take our test print, we again record the audio, we split it into segments, and we acquire the peak constellation, and we simply look for matching constellations, which constellations match the most in our database. It's a pretty simple classification scheme. And the result that we get from that is that each segment coming out in order is going to be matched up to a training segment, and we're going to have a confidence score that's equal to the number of peaks that were in common to provide that classification. So to further kind of boil down these results, we ask a couple questions. First of all, as these segments are being classified, are the results coming out in order? If we feed in chronological order, do we get results in chronological order? For each segment that doesn't come out in chronological order, we can go ahead and set the confidence score equal to -1. We know that's a bad result because 2 comes after 1, 3 comes after 2, and so forth. Furthermore, if we have our segments coming out in order, so 0, 1, 2, but the confidence scores are really low, we can go ahead and set a threshold to say, okay, if we're looking for 200 peaks in common and we get 5 in common, we're going to say that's a fluke, and we're going to go ahead and just set that equal to -1. Now, if all of the segments come out in order and they all have high confidence values, we'll go ahead and set those scores equal to the number of peaks in common. So to kind of solidify these are the kind of results that we'll get. If you look at the top graph here, this is a situation in which the testing print is the exact same as the training print, and we see consistently high calculated scores as we just discussed. Now, on the bottom graph, we manipulated the infill of the prints in several different ways. We changed the pattern and we changed the density. And you can see for the first 90 seconds of the print, everything looks fine. And that's simply because the first couple layers are exactly the same regardless of the fill. But once we get to that second 90 seconds, we begin printing the fill pattern, and we see that these values drop to very low negative values. And we can quickly see that there is some kind of error depending on what, regardless of what the error is. So to get an idea of what the error is, we want to take a look at the spatial layer. Now, the spatial layer, we simply started out by saying, let's stick an accelerometer onto the nozzle of a 3D printer and read the values off. And the issues that we ran into with that is if we wanted to look at the XYZ coordinates, we needed to perform double integration, which with noise and kind of jerkiness caused some issues. So we came up with this kind of spherical coordinate scheme, which used a linear potentiometer and a gyroscope to read out spherical coordinates, which we could then just convert to XYZ coordinates. And what we get from this is both qualitative and quantitative data. So let's look at the qualitative first. This would be something that a user would go over. If he's alerted to an error, he can take a look at what's going on. And we see two columns. On the left, we see just what's being fed into the printer, the G code, the instructions for this particular layer. And on the right, we see the spatial reconstruction. Now, the first thing you're going to notice is that the exterior dimensions don't match up. And that's something that's OK, because all we're looking at is the fill structure. And so if you take a look at the first and third rows with the low density, you can clearly see the difference between a honeycomb fill and a linear fill. That's pretty easy. Furthermore, you can easily see the difference between a low density and a high density. And where the quantitative comes in is when you're looking at high density fills and it's difficult to tell just with the human eye the difference between what your fill pattern might be. And so we take those boxes highlighted in blue and red, and we take the frequency response of the X, Y, and Z coordinates, and we see that each fill pattern is, as we might expect, going to have its own frequency profile. So we can tell the difference between those high-density print patterns. So moving on from that, we'll jump into post-production verification using the material science methods that I mentioned. And the type of 3D printing that we're working with, there are several different types and more being developed just about every day. But we're using kind of what you might think when you think 3D printing, where you have a filament, an extruder, and you build up layer by layer your design. And our idea is that what if we were able to take that filament and embed markers at certain locations within the filament that are made of certain materials. And the reason this would be helpful for us is that if we know where certain markers are within the filament, then we can predict where they're going to end up within the 3D print. And so if the print turns out how we expect it to be, all of our markers will be in place and things are good. But if there's some kind of manipulation, then we can expect that our markers will not be where we're looking for them, and those will throw up red flags and we'll say our print is not what we expect it to be. Another element of this that we want to maintain is that we don't want to change the structural integrity of the material that we're using. So we want to use micro materials, things that are not going to change the properties of any part of our print. So since we're using very small markers, micromaterials, we need some special detection methods. And the first one we're going to use is called Raman Spectroscopy. So the very quick version of what Raman Spectroscopy is you take a monochromatic light source, or a laser, and you shine it on a material, and then you measure the photons that are reflected. And the photons are going to experience a wavelength shift depending on what the material is. So you can use Raman Spectroscopy to determine what material you're looking at. And there are specific materials that are used in material science called enhancers, which you can place on top of a material, and their job is to simply increase the amplitude of the frequency of the spectral response. So what that looks like is something like this. I'll kind of walk you through this graph. We have an underlying silicon disk, and we perform Raman spectroscopy on just that disk. And the response that we get is that blue line. The blue line is very low amplitude. Then we place our gold nanorods on top of the silicon disk, and we get the red line, a little more amplitude. And then we remove the gold nanorods, and we place the DTTCI die on top of the silicon disk. This is another enhancer. And again, we get an even higher amplitude. And so if you can imagine a laser scanning across a surface, you would be able to tell when the amplitude is low, that we're just looking at silicon, and when the amplitude is higher, we're looking at either gold nanorod or DTTCI die. So to perform multiple tests, we take these graphs and we find the amplitude and standard deviation. And we're able to see that depending on the different types of enhancers versus the blank disk, which here we switched to ABS just to make it more real life for 3D printing, we see distinct clusters that we can use to say where different materials are located. Now, one of the issues that we run into here is that because we're using visible light, we're limited to about a 300 micrometer depth as long as our object is opaque. So we took a look at another type of visualization, namely CT scanning. So CT scanning you might be familiar with from medical applications. It's also useful for looking into inside of objects, and because essentially all it is a 360-degree X-ray. And here we're using a SkyScan micro CT scanner, and the micro part is very serious. We're only able to scan very small objects. So here you see a very small 3D printed cylinder. And again, we're able to use these embedding materials, such as gold nanorods. We're able to make a filament that was embedded with gold nanorods. And here you can see from the CT scan that we're able to look into the cylinder and say, look, this is a crosshatch pattern in our fill. Now, we ran into a couple issues. Namely, it is difficult to consistently have fully saturated filaments. And so we switched over to, rather than PLA and gold nanorods, we switched over, or sorry, ABS and gold nanorods, we switched to PLA and steel saturated filament. PLA is very low density. The X-rays go straight through, as you can see on the left. And steel is obviously very high density, and we can see that it's very dark on the CT scan. And so what we did was we took that cylinder and we printed 2 layers with the stainless steel filament. And we can see that those show up very clearly. Now, these are markers that are entire layers, but you can imagine that if we were to just place little dots of markers throughout the print, that it would be very easy to tell exactly where those lie in a 3D sense. So let's put all this together, the acoustic, spatial, and material layers. And we'll go back and we'll see if we can help Timmy here. So first what we're going to do is we're going to follow this prosthetic knee through the manufacturing process. We're going to identify an error using the acoustic layer. We're going to visualize it using the spatial layer to find out what it is. And we're going to take one last look before the doctor performs the procedure using the materials layer. So here we see, just like before, on the top graph, we see what the prosthetic knee should look like in the acoustic profile. Now we have many, many more columns here because this is a more complicated print than what we saw before. It takes more than 2 hours. But we see consistently high calculated scores. Now on the bottom, we have our malicious print. And we see that very quickly the scores drop off, become negative. And in fact, we're able to identify the error within about 4 to 6 minutes, when otherwise the print would have taken, again, upwards of 2 hours. So right now we don't know what the error is, but we can go to our spatial visualization and figure out what it is if we don't have direct access to the 3D printer. So we have our reference code. These are the instructions that are being sent. If the prosthetic knee is as we expect, we should see something like this. The fill pattern is linear. The density is about what we expect it to be. But in a malicious sense, we see this, and we say, oh no, we have wide open spaces, a hexagonal fill pattern, low density. This could potentially cause failure in the knee once it's in use. And so we're able to catch the issue and see exactly what it is. Now let's say that the prosthetic knee passes both acoustic and spatial tests, and we printed the fill pattern with our stainless steel filament. The doctor is able to take one last look and place it into a CT scanner and see that indeed the fill pattern is what we expect, and he can carry on with the procedure. In another view, we have 2 different layers of the stainless steel filament, and we're able to see exactly where those layers appear and in high detail. So in conclusion, first of all, Timmy gets to play his golf. We're all happy about that. And we provided an exploratory approach to side-channel verification of 3D printed models in real time and post-production. There's obviously a lot of future work to do. We're looking at implementing this in true real time and conducting more tests to really get an idea of the quality of the verification of these methods. If you have any future questions, you can shoot me an email. But does anybody have any questions right now? Sure.
Yeah, Thorsten Holz, Ruhr University Bochum. Very interesting work, but I have a question regarding especially the acoustic fingerprint. Sure. Because I think one of the advantages of 3D printing is that we can customize everything. Mm-hmm. So each knee implant will be different.
Right.
So how do you then train on because you haven't seen the model before, so how do you build the truth?
Right, so there's a couple ways that you can tackle this, and there's certainly situations where if every single print is going to be completely unique, you're right, this wouldn't be useful. But in one instance, you can say, if you have an industrial setting where you have X, Y, and Z components, and you're just switching out which predefined objects you're printing, if that makes sense, then this would be useful. Or if you have a situation where there are components of kind of like, if you have like a base material, but you're editing external features, you could also train based off of just the core that you know isn't going to change, if that makes sense. So in our knee example, you might edit the depth of the socket or things like that, but the general template is going to be essentially the same.
Mm-hmm. And a closely related thing, so for MakerBot I can see that there's this acoustic side channel, but let's say commercial 3D printers I saw, they are quiet. Did you also do some tests with the real 3D printers?
So yeah, these were all conducted with real 3D printers, and the ones that we used happen to be noisy. I'm sure there are quiet ones. Now I mentioned that there are several different types of 3D printers, and so as you scale up, you can have much larger 3D printers, which would be likely to create some type of noise. But that is an issue, that there are very quiet ones, and that would be some future work to see what we can get out of those very low amplitude acoustic signatures.
Hi, Logan Blue from the University of Florida. So I'm trying to get a sense of how precise you guys can get down to. Can you detect if someone were to put in a stress concentration point into some aspect of the print?
If they were to place a what now?
A stress concentration point. So if I were to remove a fillet from a corner, and I get a very tight corner, I can increase the stress concentration there by orders of 3 to 10x, mm-hmm. and cause failure in that sense.
Right. So I wouldn't be able to answer like exactly if that scenario would be caught. I would say if we were to catch it, one way would be with those markers. If we're able to very precisely tell where they are, regardless of what you're changing in that fillet point, our precise measurement is going to be off a little bit. So we might catch it in post-production, and depending on how far we can take the acoustic method, we may see a red flag just at the moment that you're putting in that very small deviation.
Okay, thank you.
But yeah, I wouldn't be able to say exactly how that would be caught.
All right, thank you.
Yep.
Martin Grote, Ruhr University Bochum. I would like to know if you're using acoustical side channel, how's the difference between two devices of the same model? So are there some differences between the acoustical feedback you get?
Right, so that was one thing that we weren't able to explore, is two 3D printers of the exact same model. That's what you're asking? So we weren't able to explore that. That would definitely be some future work. One interesting thing that we found was that it doesn't matter what the model itself is. So this method works whether you have a Delta printer or a Cartesian printer of different models. But yeah, that would definitely be interesting to work on, is can you train on one device and operate on another device?
Yeah, thanks. Okay, and then another one. Couldn't you not just use the amount of input material you are using in order to detect if the density of the model was reduced? So,
right, so to say this model is going to require X amount of material, and do we have that much material? We can certainly do that. And one of the keys, and I think we mentioned it in the paper, is that this isn't an end all and be all of of verification, you could definitely add that as an additional layer to say, did we just use the amount of material that we wanted to use? If no, then we have an issue. So maybe a fourth layer in there.
Okay. Thank you.
Yeah, no problem.
Hi.
Yes.
I have a question. So I'm Raman from UC San Diego. So I have a question. So how do you bind a acoustic signature to a print? Because I can just print two prints. One is the legal one and one is the malicious one. Mm-hmm. And I will just send you the acoustic signature of the legal one with the malicious print.
Right. So you're asking, is it like what's to stop somebody malicious from just training on a malicious print in the first place?
No, I mean that I suppose the manufacturer will give you a print and also the acoustic signature of the print, right?
Right.
And so how do you know that actually that is the acoustic signature of the print? I can give you another one.
Right. So how do you verify that the training itself is authentic?
Yeah.
That would be. That's a good question. I don't have a great answer for it right now. I would say if I own the printer, I could do the training, observe it, be in the room while it's happening.
But I think in your model, the whole point of the convenience is very important. That's why you send the design plan via network to the manufacturer, right?
Right. And okay, I see what you're saying. Yeah. So that all kind of falls apart if I'm able to just kind of be in the room in the first place. That's a good point. There would have to be a certain level of trust between the manufacturer and Bob in our situation. Just that the manufacturer as an entity wants to be trusted. So the manufacturer would actually hold the training files themselves. What we're not trusting here is the network, any external exploits that would be placed on the PC. But the third-party company, as an entity, we would trust.
Okay, thank you.
If there are no more questions, then I think we're ready with this session and ready for lunch. Thank you very much again, Christian.